Hello and welcome. Dear students, today we are going to discuss an important topic, that is base flow and its relation with hydrograph. Before elaborating the topic in detail, I will provide an introduction about the today's module. As you know, the plot of river discharge versus time is called a hydrograph. The rising limb of the hydrograph is the result of the precipitation in a watershed. The precipitation leads to a sharp rise in the discharge and creates a peak in the hydrograph. This is called direct runoff. After the rainfall ceases in the catchment, the discharge at a stream outlet starts decreasing to a previous condition. The hydrograph curve decreases to a lowest value, which is called as base flow. The base flow part of discharge is not contributed by precipitation. It sustains the flow in the river due to the contribution of groundwater and soil water storage. This flow in the rivers is important for maintaining the flow in the dry months and supports the ecological and economical life during the long dry seasons. Therefore, understanding the base flow and how it relates with the total flow in a river has fundamental significance in hydrology and hydrogeology. The volume of base flow, its variability and the controlling factors all help to explain the river behavior, water availability and flood and drought resilience. Thus, base flow is a key indicator of groundwater surface water interaction, which is an important part of water resource management. This module is devoted to the understanding of the concept of base flow. It also provides the learners an understanding about the separation of base flow and its modeling and how it has changed over past in India's river systems. Now, let us discuss stream flow hydrograph. A hydrograph is a graphical representation which plots the discharge versus time measured at a specific cross section of a river. The shape of the plot has huge significance for hydrologists as it helps us to understand the unique climatic and physiographic characteristics and their role in maintaining the hydrological processes. It is a fingerprint of a watershed and analyzes how rainfall is transformed into stream flow. The anatomy of hydrograph varies from basin to basin as well as with climate. Most hydrological textbooks discuss a single peaked storm hydrograph that consists of three distinct components. The rising limb is the segment or volume that represents the increase of flow after a rainfall event. The curve rapidly rises and reaches the highest point on the graph and then decreases up to the inflection point on the recession limb. The time period from the end of the rainfall to the point of inflection is called the time of concentration. The shape and slope of the rising limb is primarily influenced by the storm event and catchment characteristics. Peak flow is the highest discharge marked on the y-axis. It stays for some time depending on the nature of rainfall and watershed characteristics. The section of the hydrograph with highest flow is called the crest segment. Peak discharge occurs only when runoff from the most distant parts of the watershed reaches the gauging station. The volume of water between the two inflection points represents the peak flow. Recession limb or falling limb is the part that extends from the second inflection point of the hydrograph. The inflection point indicates a change in the slope and marks the termination of the direct rainfall contribution. Unlike the first limb, the recession limb is not dependent on the rain event, but is directly governed by the interaction between river flow and aquifer storage. It also depends on aquifer properties such as storage coefficient and permeability. Now, let us discuss base flow and direct runoff. The entire flow in a river during or after an rainfall event is called the total runoff hydrograph. It is the sum of two distinct flow components. One part occurs directly in response to the rainfall and causes a sudden rise in the volume of river. This is called the direct runoff or the surface flow. Direct runoff develops and travels from all sides of the catchment to the outlet. It can be delayed or reaches very abruptly as in flash floods. Another part of the flow is the contribution from the groundwater. This continuously and smoothly adds to the hydrograph without any major role of rainfall event, and it is called the base flow. The nature of base flow and its total contribution to the river flow can be modeled using the discharge data of the recession limb. The ratio of base flow volume to the total river flow is termed as base flow index. It can be 0, meaning no base flow, as in semi-arid and arid rivers. The index is generally higher, greater than 0.5 in perennial Himalayan rivers like the Ganga, Brahmaputra and Indus. The major reason for high percentage of base flow is the high recharge, glacial contribution and vast porous alluvial aquifers. For seasonal rivers like those in peninsular India such as Krishna and Pennar, the base flow index is lower, less than 0.4. These rivers mainly flow through hard rock aquifers which have limited aquifer storage compared to the alluvial aquifers. The semi-arid climate, less rainfall and more evapotranspiration is also responsible for low base flow. Understanding the base flow is important for hydrologists and watershed planners in many respects. Imagine a river flowing after months of dryness or no rainfall. Where from this river flow comes from? Hydrologists call this water as base flow and identify that its sources from groundwater seepage and the slow drainage of soil moisture. The water has infiltrated the soil and percolated into aquifers over a period of time and then slowly comes back to become part of surface hydrology in river channels. Therefore, base flow is the water coming from the savings account or lifeline of a river or watershed. While rainfall and runoff are like event based cash inflows, base flow represents the gradual release of stored groundwater during dry periods. The mechanism by which base flow is maintained is critical for the health of a river system. This maintains a long-term flow in rivers around the world during dry spells. Now, let us discuss the factors influencing base flow. While surface features of the watershed largely determine direct runoff, base flow is mainly governed by the interaction of surface water and groundwater systems. However, this interaction is a complex process and is governed by the nature of land surface, hydrogeological characteristics and the climatic conditions. Understanding these factors and their role on the base flow variability is essential for managing river hydrology in India, where diverse landscape and geology affect base flow from basin to basin. The major factors affecting base flow include: geology is the most dominant factor influencing base flow. The type of rocks, their porosity and permeability and presence of fractures and faults impact base flow. Catchments having highly porous and permeable lithology such as sandstones or limestones have high infiltration factor, and groundwater reserves. This storage releases water slowly to the rivers and sustains high base flow. The Indo-Gangetic plains have vast, deep and highly porous sand and silt aquifers. They feed the river systems like the Ganga and Yamuna even during non-monsoon months. While in peninsular shield nearly 60% of the lithology is hard rock terrains. They are composed of basalt or ductine traps and granites which have low primary porosity and limits the storage and yield of water. This causes the flow in most of the rivers like the Godavari or Krishna to reduce significantly in summer. Climate also impacts base flow. Type of rainfall, its intensity and duration affect the rate of recharge. Low intensity and long duration rainfall factors infiltration, that is stored in the aquifers and released as base flow. This occurs mainly in the Himalayas and during winter rains or retreating monsoons. On the other hand, high intensity storms which are common during the Indian summer monsoon exceed the infiltration capacity and cause high runoff, low recharge and low base flow. Very high evapotranspiration like in Rajasthan causes no or very low base flow in the rivers like Luni. Physiographic characteristics of a watershed also impact the base flow. Steep land slope inhibits infiltration and groundwater storage and thus less base flow. In comparison, the flatter watersheds allow percolation that releases later as base flow. In addition, watersheds with coarse soils have high infiltration rates and high base flow. In comparison, the fine soils, clays or hard soils reduce base flow contribution to the rivers. Vegetation and land cover control intensity of falling rain, interception and infiltration. Conversely, their root systems make soils loose and develop sponge effect, due to which more water gets stored that later releases as base flow. Deforestation in such areas has reduced the base flow as seen in some watersheds in the Western Ghats. Anthropogenic factors have stressed the water storage and flow processes. Excessive groundwater pumping lowers the water table below the riverbed, reversing the hydraulic gradient and direction of the flow. Thus, the perennial rivers are becoming losing ones and turning into seasonal streams. Urbanization also reduces infiltration, groundwater storage and base flow in some rivers. Now, let us discuss base flow separation from a hydrograph. Separating base flow from the total runoff hydrograph has huge significance for water management, agriculture management, flood forecasting, reservoir engineering, etc. Base flow separation is the analytical process that allows hydrology experts to estimate the contribution from groundwater in any river system. Then how is the base flow estimated from the total runoff? For this, there is no single or universal method or technique. Several approaches used by hydrologists depend on the data density, scale of study, purpose of analysis and expert experience. It is not so simple to identify and estimate the base flow volume and divide it from direct runoff, but it is important that all the methods are arbitrary in nature and the results are acceptable, because the errors do not affect the overall aim. The commonly used methods include graphical, based on stream flow data and experience of the modeler; hydrological simulations based on hydrometeorological data; tracer based methods based on stream flow and tracer values injected and received; conductivity mass balance based on stream flow data and water conductivity values; automatic methods based on stream flow data. Some of the most commonly used graphical methods are explained for the readers. First, straight line method, also called as fixed base method. How is it done? The hydrograph is checked for any wrong data and all the single peaked hydrographs are plotted on a graph. Now locate the point on the rising limb where the graph begins to rise, mostly the time when the storm onsets. Similarly, on the recession limb, locate the point where the discharge again starts to return to the normal condition. Draw a line joining the 2 points. The sum of the discharge below this line is treated as base flow. The advantage is that it is a simple method suitable for quick analysis, but it often oversimplifies groundwater behavior and may overestimate runoff. Second, variable slope method. Observe the hydrograph and locate a point B on the recession limb. The point generally lies n days after the peak flow. N is calculated using an empirical equation, that is n is equal to 0.83 into A raised to power 0.2, where A is area of basin in square kilometers. Now extend the previous recession curve smoothly to the point directly under the peak flow. Draw a straight line from this point to B. This is the more realistic approach because the recession curve would behave approximately the same way under non-monsoon conditions. The next method is curve extension method. This method is based on the assumption that when direct runoff volume increases, the base flow amount also increases due to infiltration of some rainfall amount. Thus, the base flow curve will slightly increase along with the rising limb, although it is not always correct, but it could be true in some highly fractured and karstified terrains where infiltrated water reaches the stream fairly rapidly. How this method estimates the base flow? Draw the recession limb after the peak flow backward smoothly to the point right below the inflection point. Now sketch a smooth curved line ACB from the previous recession curve to this point. Another method is digital filtering methods. Modern base flow separation methods use computer based digital filters, for example Eckert filter. The methods mathematically separate the background data or low frequency base flow from the high frequency values. The widely used Eckert's filter depends on two values, the recession constant and the maximum allowable long term ratio of base flow. Chapman algorithms are preferred as they treat stream flow as a signal and separate high frequency runoff from low frequency base flow. The Eckert recursive digital filter methods are used for efficient long term data sets. It has been used in basins such as Ganga, Godavari and Narmada to assess groundwater surface water interactions. Now let us discuss modeling of base flow. Over decades of research, hydrologists use several curves to represent the receding trend of base flow. The most important and widely used is the simple exponential equation developed by Mallet in 1905. The equation assumes that the water withdrawal from the catchment has no new input from the precipitation. The curve is described exponentially and expressed mathematically as Qt is equal to Q0 e raised power minus At or Q0 raised power Kt, where Q0 is the initial discharge and Qt is the discharge at any time. K e raised power minus A is a constant called the recession coefficient. The curve plotted on a semi-log paper forms a straight line with a slope of minus A. This is called a master recession curve or master depletion curve. Combining all the recession curves by statistical techniques gives a master curve that gives an average picture of the depletion. The curve simply represents how a river flow declines over time, that is rate of change of Q with time or dQ by dt. Master recession curve has been widely used to reveal the base flow contribution to the streams, flood analysis, drought and manage water resources. In addition, chemical tracers and isotopes provide the accurate distinction between the water types, but they require extensive field and analytical data. During flooding conditions, the water level in a river is too high. The stream becomes a losing one and feeds the permeable banks. This is called bank storage. During the recession period, some base flow also comes from the bank storage, although small and temporary. This is called negative base flow. Now let us discuss importance of studying base flow. Understanding base flow is necessary for solving many real world problems. For a student of hydrology, it is more than just a theoretical component. It supports both scientific understanding and practical water management. It is used to quantify groundwater contribution to surface hydrology. In many rivers, especially in Himalaya, base flow contributes 30 to 60% of annual discharge and nearly 100% of dry season flow in some watersheds. Hydrological drought is defined when water level in rivers, reservoirs and groundwater declines very badly and affects the communities. It often follows months of meteorological drought. The decrease of base flow in rivers is an indication of the hydrological drought. Thus, understanding base flow will help to manage water shortages and develop strategies for resilient water basins. The slope and trend of recession curve is a diagnostic tool to reveal the permeability and storage capacity of the aquifers. Base flow studies are carried out for water resource planning, groundwater recharge and storage, define sustainable abstraction limits and ecosystem protection. Its variability also reflects the change in climate and land use. River water carries huge minerals and pollutants. Therefore, base flow provides the necessary volume to dilute urban and industrial effluents during the dry periods. Now, base flow changes in Indian rivers. The base flow in Indian rivers shows a varied behavior during the past decades. The main factors include the varied climate, geology, land use and human factors. Base flow in Himalayan rivers is very high and contributes 40 to 70% to the total flow, while in the peninsular rivers it contributes 30 to 70% of the annual stream flow. Over centuries, the rivers were flowing naturally as gaining streams without showing any variability in direct runoff and base flow components. However, after industrial revolution, the climate has been modified and many human activities have directly affected the water resources. Due to this, many rivers have reversed the hydrodynamic regimes and become losing streams, that is, rivers lose water to the aquifers. For example, the Indus river system is facing a critical hydrological shift. The meltwater contributes 40 to 60% of the annual flow. Late summer and autumn months are the normal base flow months. However, peak base flow is coming in spring, that is May, June. The most visible impact is seen at the Kotri barrage at the Indus Delta. Nowadays, the dry season flow is 0 or negligible for 10 months as compared to the past decades due to human factors like pumping, urbanization, deforestation and water use. River flow and base flow have decreased. Similarly, the human consumption of groundwater has also impacted the river base flow in the northern India. Due to this, the water table has declined several feet and is below the river bed. Dear students, this was all about today's program. Hope you have enjoyed it well. Thank you for watching.